Okay, we're going to start chapter 2. And oh, help if I turn to it's Friday afternoon, it's okay. So we're going to start chapter 2 today. We'll finish chapter 2 on Monday. And we're going to be looking at energy production for the next few classes, right? Chapter 3 is also energy production. Anyone got good plans for the weekend? Parties? No plans? Bike rides? Hiking? Going to be studying Xfield. Not that either. Alright, here we go. So, start looking at anaerobic energy production. Alright? And our learning objectives for this chapter, make sure that you look at those when we finish this chapter. If you look back at this list and you go, huh, that's not ringing a bell, then make sure that you check into it. Alright? So energy production, two terms, either bioenergetics or metabolism. They really mean the same thing, depends which book you're looking at. And it's just looking at converting energy from food into energy we can use. Right? So if you remember back to biology in school, the sun's the source of energy on this planet. Plants use sunlight to convert energy into carbohydrates. We then use the carbohydrate, or another animal uses the carbohydrate, and we get our food from plants or from those animals. So all that energy all kind of cycles around and links up. Either chemical, electrical, heat, mechanical, we can't lose it. We can only change it into a different form. So, our first energy source then that we're going to look at is carbohydrate. Carbohydrate is a very quick, easy to get at source of energy for humans. Right? The way that we convert carbohydrate is very quick. And we get it in our diet in 3 different forms: mono, di, polysaccharides. Monos are simple sugars: glucose, fructose, galactose. Disaccharides, 2 monosaccharides stuck together. And then polysaccharides are the things that we think of as starches: potatoes, rice. Cellulose is a polysaccharide, not digestible, we pass it through the system. And glycogen, which is our storage form of carbohydrates. So in humans, we store the majority of our carbohydrate as glycogen. Right? It can be stored either in the liver or in the muscle tissue directly. When we break glycogen down, that process is called glycogenolysis. breaking down glycogen into glucose. So if it's stored in the liver, we break it down into glucose, we pump the glucose into the bloodstream, it moves around the body to the muscle that needs it. If we break it down in the muscle, it goes directly into energy production. So it just depends where it's coming from. And if we've got too much glucose in our system, we can store it as glycogen through glycogenesis. Right? So glucose is a simple sugar, monosaccharide, and we often use the term blood sugar. That's glucose in our body. Right? We can use that glucose that's in the blood, we can move it into the muscle tissue and use it for energy, or we can break down the glycogen that's in the muscle tissue and use it to make energy. Monosaccharides are a simple ring. They have 6 carbons in them. That's the important bit. This isn't a chemistry lesson. We do not need to know this. Right? We need to know it has 6 carbons. Okay? We said glycogen's a storage form in animals. It's not the way plants store carbs, but it's the way we do it. And this is what a glycogen molecule looks like, and each one of these little red areas is a glucose. So we've got loads and loads and loads of glucoses together, we get a large molecule that is glycogen. All right, large-ish. And it's a really important energy store for creating metabolism at rest and in exercise. So if I want to, why do we need energy? Let's step back. As a human, what do we use energy for in our body? Everything. Okay, be a little more specific.
Keep your body warm.
To keep us warm, to move. What else? Break down foods, right? Digestion uses energy. Okay. Breathing uses energy. Okay. So glucose and glycogen are important whether we're moving or not. Because even at rest, we need energy just to do other things, you know, keep the body going. So our next energy source is fats. And again, we don't need to know this is stearic acid, but we don't need to know that. But, oops. But we do need to recognize the fact that when I look at a fat molecule, I have way, way, way more than 6 carbons, right? Because next week, how many carbons are in the molecule plays a role in how much energy I can get from that molecule, right? So, yes, humans can use fat as an energy source under certain circumstances. Right? And fats, we can get fats in our diet from either plants or from animals. The terminology that we're interested in when we're looking at fats as an energy source is either a fatty acid, so fat is carried around our bloodstream as a fatty acid, and they have 4 to 24 carbon atoms. And we have saturated fatty acids, monosaturated fatty acids, polyunsaturated fatty acids. Saturated are the bad guys. They're the ones we want to try to not cut out of your diet altogether, but you want to limit the amount of saturated fats. Monos and polys both have health benefits. So you want to increase the amount of those types of fats within your fat intake. Triglyceride is our storage form, so triglyceride is like glycogen, right? Glycogen is carbohydrate storage form, triglyceride is a fat storage form. And we break that stored fat down by a process called lipolysis. Right? We store most of our fat in specialized fat cells, but you can also find it in other tissues as well. If you buy a nice marbled steak, it's marbled because it has fat in it. Our muscle tissue has fat in it, right? But not as most of it is in these specialized fat cells. And when we break it down using lipolysis, then what we get is a glycerol molecule and 3 of these fatty acids. So the fatty acids get dumped into the bloodstream, go around to the muscle tissue, and the glycerol goes to the liver and gets turned into glucose, which then gets dumped in the bloodstream, which then goes in. Right? So there's a lot of energy in a fat molecule that we can get at and use. And what we're going to look at here is the fact that fat stores in the body are abundant, right? They can't be depleted, and therefore fat or lack of fat is never a source of fatigue, okay? So if we look at this table, that it always amazes me every semester when we look at this table. So here's my carbohydrate stores, okay? So in the liver I have about 110, so about 450, 500 calories worth of energy stored as carbohydrate in my liver. About 2,000 calories in my muscles, and somewhere around 50 to 80 calories in your bloodstream. So your bloodstream really isn't a very effective storage unit for carbohydrate. Yes, we have some there, but it's not where we store it, right? So all in all then, we've got somewhere around 2,500, 2,600 calories of carbohydrate. And that's it. It's a very limited amount of carbs that we're able to keep in our body at any one time. When we look at fat, however, in our subcutaneous and visceral fat areas, remember we store fat under our skin, and we've also got that wrapped around our organs, keeping them safe, right? About 73,000, 73,500 calories. And then in the muscles, somewhere around 1,500 calories in stored fat energy. So about 75,000 in total, okay? And the interesting thing when you look at the table is that this is based on someone who's 143 pounds with 12% body fat. 12% body fat. So this is a very lean person, okay? And they've got 73,500 calories worth of fat stored in their body. So you can't run out. Okay? It's really, you've got to be in serious doo-doo to get to the point where you don't have enough fat, like the girl that we were looking at the other day, okay? So we have carbs, we have fats. The other energy source that we can use is proteins. But you've got to be a little bit careful about how you think about proteins when it comes to energy production, all right? There's about 20 or so amino acids which are the building blocks that make proteins. And those amino acids are either essential or non-essential. If they're essential, if they're labeled essential, and there's 9 of those, that means as adults, there's actually, I think there's 10 when you're looking at children who are younger than puberty. But in adults, there's 9. And those are amino acids that the body can't make for itself. That means that you have to ingest them within your diet. Right? The other group, the non-essential, can be made by the body. If it has to, it can put other bits and pieces together and make those amino acids. So if you go for a day or a couple of days or a week without them, you're not going to get really sick. You're not going to see a big detriment in performance or health, but you can't go without these. The thing to pay attention to at the moment is that we only use protein to provide energy in a very small range of activities. All right? Typically, humans use protein to build things, mend things, fix things. Right? So when you train and you break down muscles as you're training, you have to have protein to fix them all again. If I want to grow, I need proteins. Right? Anything that needs proteins can't work if we don't provide the protein. All right? But we don't really use it for energy. We can, if I run a marathon, right, 26 miles, 4+ hours if I tried it, I'm sure, right? In that 4 hours, all that work that I do in that 4 hours running, only about 5% of the energy that I need to do that work comes from protein. Almost all of it will come from fats and some from carbs at either end. Right? So if I'm an anaerobic athlete, if I run, jump, throw, you do not use protein for energy. Okay? And we're going to come back and talk about that more during the semester, because right now there's a big push on these high protein diets. And there are all kinds of adverts out there saying, protein gives you energy, right? How many times anybody heard, well, make sure that you eat your protein, it will give you energy. Not in the way they mean. Because typically when they say, oh, protein gives you energy, they mean, oh, it's going to make you can run and jump and keep going all day because you ate that protein. Well, it doesn't do anything for any of that. You don't use protein at all for any of that. So, bless you. So just be a little careful as you think about protein, because in the media at the moment we're getting some very mixed messages about what protein can do for you as a person, or particularly an athlete. Right? Okay, with me so far. It's Friday afternoon, guys. Everybody awake? We need a little wiggle. Stand up. Stretch. Balance on one foot. Balance on the other. Okay, sit there. A new Friday afternoon stretch session. Decided they're going to make us have class on Friday afternoon. We've got to keep ourselves going. All right, so carbs, fats, proteins. We eat those somehow we've got to get at the energy that those foods hold and get it into our muscles, right? One of the things that we need to help do that are enzymes. Enzymes are proteins that facilitate chemical reactions in the body, including metabolism, energy production. Right? So they do not make the reaction happen. They don't make the reaction happen, but they help the reaction, because what they do is they lower the energy requirement for that reaction so it can occur more easily. All right? That's called the energy of activation. And they lower how much energy is needed, and therefore the energy can occur more quickly. Right? And they work, and this, you really got to get this sorted out. This diagram is in your book on page 31, thank you. So, the fact that we can't see it is not very helpful, but enzymes have a particular shape, and so we use the term lock and key mechanism. Every enzyme is very specific to a particular molecule, all right? So it has a certain shape that's fixed, and a particular molecule will fit that shape, okay? And it helps speed up the reaction for breaking that molecule down if you're looking at catabolic reactions, or it might help an anabolic reaction. It'll fit two molecules and it will facilitate putting them together to create another molecule. All right? So what we need to pay attention to here is that they don't cause the effect, they help the process, and they're very, very fussy. Right? Enzymes are really, really fussy. So, enzymes like a particular range of temperature. They like a particular acidity level within the cell. Right? So, when we exercise, we raise the temperature and we raise the acidity. So that impacts what enzymes are able to do. So as we start looking at the energy systems, you'll see that temperature increase and acidity increase can impact how much energy I can produce. They also sometimes need coenzymes, things that help them, like B vitamins. So if your diet is particularly low in B vitamins, you might find that you're feeling fatigued because you're unable to make energy effectively. ATP, adenosine triphosphate, is the energy molecule for humans. It's the only thing. Right? It's slightly ineffective in my mind. It's not the most efficient use of the energy that we have in our body when the only way we can get at it is through one molecule. But that's the way we've developed, so that's what we have. Okay? ATP, it's not the only molecule that holds energy, it's the only one we can get at the energy. Okay? So, at the end of anaerobic or aerobic metabolism, the goal is production of ATP. And ATP is built of an adenine and a ribose, and then here's our key, our 3 inorganic phosphates. So we get ATP. Okay, and we can break it down. And the enzyme that helps us break down ATP is ATPase. Right? So the thing that makes ATP special is I've got my adenosine here, and it's attached to 3 inorganic phosphates. Is this big enough? Can you see this? Do I have to write bigger?
I got it.
You got it?
Yeah.
All right. So this third energy bond is the key. All right? That's the energy that we can use for muscle contraction. We've got other energy bonds here, but we can't use them. We can only use this one. So when we break it down, we get ADP, adenosine diphosphate, plus an inorganic phosphate, plus energy. And actually, you need water in here, and we also get hydrogen ions, and they're the things that start to cause the problem because they're the acidic thing. All right? Does that make sense? So adenosine, bless you. Adenosine diphosphate has energy, but we can't use it. So once we've broken it down to ATP and we have ADP, now we have to get energy to stick the inorganic phosphate back on there. With me? Making sense? So what happens then? At the end of it, right? Because we don't have very much of this stored. Which energy system we use? We have 3. Which one we use depends upon how much energy I need at that particular time. Right? So how long is the piece of work that I have to do? So we have enough ATP as adenosine triphosphate, in our muscle cells for somewhere around 5 seconds worth of work, 5 to 10 seconds, not very much time. So if you've got to get up and go out the room and go down the corridor and go to another classroom, stored ATP isn't going to get you there, because that will take you longer than 5 seconds. But if I'm only working for 20 seconds, 25 seconds, possibly up to 30 seconds, I don't have enough time to get at that energy that's in the carbohydrate that we talked about. Because whilst glucose and glycogen are not very big molecules, they still take time to break down. So the first system that we'll come to is the ATP-PC system. Right? What happens if I'm breaking down ATP and I'm getting this energy for muscle contraction? What happens when I run out of ATP? So that's the first thing we're going to look at. And then the second bit is, okay, by about 25 seconds or so, if I'm still moving, I've had enough time to start breaking down some glucose and some glycogen. And so what is system number 2, where I can actually utilize carbohydrate and I can get energy from carbohydrate to make my muscles move. have to start using oxygen. And so we've got a whole other system that can generate ATP for a long, long period of time. Okay, so system 1, ATP-PC. I have enough ATP for somewhere around 5 to 10 seconds, depending upon the individual, what kind of training they do. And then PC stands for phosphocreatine. Note that if you are looking at an old source, so if you're looking online for information, or you're looking at an old textbook or an old coaching journal, PC used to be called CP. It was creatine phosphate. Somewhere between my undergrad and my graduate, which was a big long break in time, it switched over. All right, I don't know why. So it's now PC, phosphocreatine. All right, phosphocreatine is another molecule that's in the muscle cell that holds energy. Okay, and we have generally enough phosphocreatine to do around 15 to 20 seconds. All right, so if we put these two together, we've got somewhere around 30 seconds. That's the top end of what this system can manage with. Yes? All right, so ATP. I'm going to break it down to ADP, PI, and energy. If I want to build the ATP back, I have to add in energy to reverse that and go back to ATP. Phosphocreatine and the enzyme that facilitates the breakdown of phosphocreatine is creatine kinase. So often what you will find is that the enzyme name says the thing it's breaking down with an A's on the end. So if I see a word that finishes in ASE, that's an enzyme. So phosphocreatine breaks down into creatine plus an inorganic phosphate plus energy. So what the body does, because it can't use this energy because it came from the wrong molecule. It's very odd, right? But that's the way it goes. So what the body does is it steals this energy and it feeds it back in here so that I can come back to ATP. So it's kind of inefficient, because if I've got this energy here, why can't I just use this energy to make muscles contract? But that's not what humans do. They can only use this energy to make muscles contract, right? With me so far? We're doing all right. Okay. What we find, however, is that in events, in sport events that predominantly use system number one, the ATP PC system, that generally they don't work at a level, they don't go to 30 seconds. Like most of the things we see happen are 20 seconds, 22 seconds. Okay. People start to lose power. So if you are sprinting as hard as you can for 30 seconds, towards the end of the 30 seconds, you slow down. Right? Think how fast 100 meters is. World record 100 meters, 8 point something or other, something silly. So if you run as fast as you can, chances are, by 30 seconds, you are slowing down. Right? Because at 30 seconds, you're not running as fast as you were at 10 seconds for 100 meters. Period. No one. Right? If I'm slowing down means the system is getting fatigued. It's not able to maintain ATP production at the level it needs to work that hard. Right? So fatigue makes us slow down. The fatigue, though, generally is not because we ran out of the ATP and the PC. What the research is showing is that the fatigue, when you look at a sprinter, that fatigue is caused by the inorganic phosphate and the hydrogen that gets released from this system, because both of those are acidic. What did I say a few minutes ago? What doesn't like acidity? Close. Enzymes. Good. Right? So, if I suddenly create a whole ton of acid, the enzymes slow down. And if the enzymes slow down, ATP production slows down. Therefore, force is lower. Therefore, I slow down. So, probably, when we're looking at force fatigue issues in sprinters, it's probably going to be because of these inorganic phosphates and the hydrogen ions. That's relatively new that we're finding this out, because a lot of people assume that because the amount of ATP and PC that's stored in the muscle is so small that you just run out of that at 25 seconds. So, if I do start running out of phosphocreatine, or if I've run 200 meters and I'm really, really low on phosphocreatine, if I want to, tell me if you can't see any of these colors, if I want to do this, right, if I break down all the phosphocreatine in the muscle cell, and I want to rebuild phosphocreatine, what do I need? Right? So when we're in recovery from doing a short, hard run, during recovery, somehow we have to get hold of some energy so that we can rebuild phosphocreatine in the muscle cell. And we're going to come back and look at, well, where the heck does that come from now? Because we don't have any of this left, and we don't have any of this left. So where's this energy coming from to rebuild them all and put them all back together for the next sprint? Right? This is why XPhys is so fun. Because it seems like it's so simple, and then when you start looking at it, it's like, wow, that is so cool. How does our body do that? And we just use it every day. We run around every day. We just assume that when I start running, I'm going to be able to run. Where did that energy come from to run? Right? So it's really a cool topic to start looking at, well, how did that happen? Creatine supplementation then would seem logical, right? If I'm using a system that needs creatine to make a storage form of energy, if I feed the system more creatine, ergo I would have more storage form, right? If you look, however, at the information on page 34, what they're finding is that it doesn't seem to be quite as effective as people have thought they were. Firstly, obviously, the only people it would help at all is athletes that are doing an event that's less than 30 seconds. So, if you're a 400-meter runner, or if you're a gymnast, or, right, then this doesn't help. If you're a tennis player, it's not going to help. Throwers, jumpers, sprinters, weight training within, right, it might help. What they're finding, though, is that when you take creatine as a supplement, you start to store more water, you hold more water. So you put on weight when you start taking it because you put on water mass, water weight, right? So that's problematical if I'm a sprinter because my mass impacts how fast I can run, right? If I suddenly put on 5 pounds in a very short period of time, that is going to impact my 100-meter time, 10-yard time, whatever it is you're looking at, all right? So that's the first thing. Then what they're finding is that when it helps performance, the performance improvements that they're seeing are somewhere in the region of 10%. So the impact on performance is relatively small, depending on the level of athlete you are. Because a 10% improvement in your performance might make a massive difference if you're top class. Okay? But there are some inconsistencies with how useful really is taking creatine as a supplement. Right? It might help you train. I suspect what's going on is using the creatine might help you train short, sharp power training, and the training makes your performance a little bit better. Right? So maybe it's only worth taking the creatine supplement in the training period in your program that is for power, not for strength or for endurance, right? So it might not be, it's not an all year, it's a part of a program, possibly. The other thing is, anyone with any kind of kidney issues, renal issues, shouldn't be taking creatine, because it stresses the kidneys. Okay? All right, so on Monday then, we'll pick up looking at System 1. What happens in System 1 if I train it? Because we assume that if we're training something, it's going to improve. So what is it that changes in the system when we train? All right? Look it over, guys, because at this point, over the next couple of weeks, the stuff we're doing is very abstract. It's not stuff that we can see easily, all right? I can give you examples, but I can't show it to you. So that means that if you miss a piece of it, it's going to impact till we get to the point where we go, okay, how do I create a training program? Then we can see a training program, right? So look it over, please, because if you miss this, then we're going to go on System 2, and System 2 doesn't make sense if System 1 didn't make sense. Okay? All right. Have a great weekend.
Thank you, Cheryl.
Thank you.